All right, this is part 2. So the cusp or sharp point is not the only time in calculus that we can see issues with differentiability. Again, that is the ability to take the derivative, to find the slope of the curve, to find the instantaneous rate of change. There's a second issue at play, and that has to do with continuity. Now, what I'm about to do, just so you're aware, this is not me making some context. You'll see some context in the homework. This is me just trying to explain the idea behind continuity with some very hypothetical made-up functions that are just instructive to make a point, not intended to be practical or applicable to a real-life context. Here's what I mean. Imagine a function that behaves as follows. Good old xy axes here, and imagine a function that behaves like this. You might have seen functions like this at some point in, say, a college algebra course where we have what's called a vertical asymptote. So functions like this where there's division by 0 is where this would occur. But here's what we would say about such a function. We would say that the function evaluated at a doesn't even exist. You saw this again come up with rational functions like fraction, algebraic fraction functions, where the denominator, if a was inputted, was plugged in, you'd get a division by 0. So we would say f of a doesn't even exist. So this function, while it's a function, perfectly legitimate function, sometimes it does come up in real life stuff, but this function would not be differentiable at x equals a because the function's not even continuous at x equals a. Now I'm throwing the word continuous out right now, fully aware that we haven't exactly defined what it is, but let me give you just the quick kind of simplistic view. If I was to draw this function, as you saw me do a minute ago, I would draw, not have to pick up my pencil, but when I got to x equals a, I'd have to pick up my pencil and then continue drawing this graph. So at x equals a, where I had to pick up my pencil, we lost continuity in this function. So this function is continuous everywhere except at x equals a. And the reason it's not continuous at x equals a is because the function doesn't even exist at x equals a because of that vertical asymptote I threw in there. Now I'm going to color code here a little bit for fun. Let me give you another function. Imagine a function like this. Good old xy plane again, and I'm just going to make up some values here. Say this was 3, say this was 1, x equals a. So, a couple of questions first of all. Suppose I asked you to evaluate this function at a. Notice no limits. This is how we mathematically say x is actually equal to a. Evaluate this function if you input an a. Well, if you input an a, don't look there. Open circle means there's nothing really there. Look there. At x equals a, the output is 3. So the function exists at x equals a. That is, if you input an a, you output a 3. Function exists at x equals a. However, there's still a continuity issue here. Notice, I can draw this function continuously until I get to x equals a. Pick up your pencil, continue drawing the function. So there is a continuity issue at x equals a, but the issue is different than here. The issue here was the function didn't even exist at x equals a. The issue here is, here it comes. Imagine the limit as x approaches a. Now remember, with limits, you have to think about approaching a from both the right and the left. And in order for the limit to exist, we have to get the same output value as we approach from both the left and the right. Let's explore that and see. Suppose you approach from the right. As x approaches a from the right, so as x gets closer and closer and closer and closer, but not equal to a, as x gets closer and closer and closer to a, this function gets closer and closer and closer to 1. What if we approach a from the left? As x gets closer and closer and closer and closer to a from the left side of a, but not equal to a, this function gets closer and closer and closer and closer to 3. So on the one side, the output value gets closer to 1 as x gets close to a. On the other side, the output value gets close to 3 as x gets close to a. And so therefore, we would say that this limit does not even exist. And so there you go. The reason this function is not continuous at x equals a is because the limit doesn't exist at x equals a. So far you've got two things. Thing number one, a function can be discontinuous, can be not continuous at x equals a if the function doesn't even exist at a, like in an asymptote. Or a function can be discontinuous at x equals a if the function exists at a, that's not the problem, the output is 3. But if the limit doesn't exist, you could have this discontinuity at x equals a. But there's a third. And the third situation would look something like this. Now again, I want to say before I draw this that I'm making up these functions for instructive purposes, not for anything practical. So imagine a function that behaves like this. All right, this function also has continuity issues at x equals a. Notice I can draw this graph continuously until I get to x equals a, pick up my pencil, place my dot, come back up here, continue drawing my function. We do have a continuity issue at x equals a, but for different reasons than here, let me play it out. First, does the function even exist at x equals a? Certainly it does. If we input an a, we output a 1. So the function exists at x equals a, unlike we had over here, so that's not the issue. Second issue, what about the limit as x approaches a? Again, we have to think about coming from both sides. Let's start with the right. As x approaches a from the right side of a, but not equal to a, just getting really, really close to a, as x approaches a from the right side of a, this function's getting closer and closer and closer to. Now remember, we're not equal to a, we're just a hair's width to the right of a. This function's getting closer to 3. And likewise, if x approaches a from the left side of a, as x gets closer and closer and closer to a, this function gets closer and closer and closer to 3. And since we have the same limiting value from both sides, we would say the limit as x approaches a of f of x is indeed 3. We come to 3 from both sides. As x gets, the input gets close to a, the output gets close to 3. But when x is equal to a, the output is equal to 1, and that is where we have the issue. The issue is the function exists, unlike here. The issue is the limit exists, unlike here. But the issue is this. In order for a function to be continuous, what happens at x equals a has to be the same as what happens when x is nearby to a. So here's what we say. In order for a function to be continuous at x equals a, f of a has to equal the limit as x approaches a. Both of those two things are equal, the function's continuous at x equals a. So, to recap, what I've shown you is that there's 3 things that we should check to mathematically show that a function is or is not continuous at some x value. First thing to check, in order for a function to be continuous at x equals a, the function has to exist at x equals a. Let me just capture that. F of a must exist. If the function doesn't even exist, the function's not continuous. And oh, by the way, if the function's not continuous at x equals a, it is not differentiable at x equals a. Second thing, perhaps the function exists at x equals a, but there's still a discontinuity. Why? Maybe it's because the limit as x approaches a does not exist. So in order for a function to be continuous at x equals a, this has to be true and this has to be true. If this ain't true, like in this case, the limit does not exist, then the function is discontinuous at x equals a. And again, if the function is discontinuous, the function is not differentiable at x equals a. And then finally, the third thing is this. Maybe the function exists at x equals a, maybe the limit exists at x equals a, as x approaches a, but the function is still discontinuous. And the third and final situation you could see is this. Not only does the function at a have to exist, not only does the limit as x approach a have to exist, but those two things have to be the same. So imagine this. Imagine this point went from here to here. Then this would be 3, this would be 3, this would be 3, this would be 3, everything would be 3, and we'd have that nice perfect continuity right through x equals a. So those are the 3 things we want to check when we're looking for continuity. Now, I like to say all of these functions are continuous. In fact, they're all continuous everywhere all the time, except where they're not. This function is continuous all the time. You could go through this set of 3 things at x equals a and find out that this function is continuous. This function is continuous everywhere except at a. This function is continuous everywhere except at a. This function, going back to this version, this function is continuous everywhere except at a. In order to show continuity everywhere, we would have to have this situation where f of a exists, the limit as x approaches a exists, and those two things are exactly the same. Then we have continuity and we have differentiability. So there you go. There's a continuity, differentiability recap.